All right, parametric equations. They talk about the fact that we introduced these in the first chapter. Actually, parametric equations were introduced there with a third variable involved. Typically, time is your third variable that we're talking about here. It has a more complete model, basically, for like a projectile. They give an example here. X of t is 24t and y of t is negative 16t squared plus 32t. And then they give you specific times, 0 seconds, half a second, 1 second, 3 halves, 2, etc. Or minutes or whatever your time is in. And so basically what you're doing is you have an xy that generates the graph, but the xy is based on a third variable time. And that's the variable that's going into your xy equations to generate your xy coordinates for this. And so they have the example at the top of kicking a soccer ball. Kicking a ball, throwing a ball, those are your standard ones for stuff like this. Rockets are some of them. And so basically they're saying, well, at time 0, both of these were 0, 0. The ball was on the ground, right? After half a second, it had been kicked. And so then they have a horizontal movement and a vertical movement on this ball that's happening after t seconds, right? It's going to go up, but it's also going to go right at the same time. And at some point, it's actually going to peak on your height and come back down, whereas your x value is actually continuing to increase. All right? And so you'll see this negative 16t. Your gravitational pull is what's going on here. And so that is, I think gravity is what, your 32. And this is the derivative if you get into calculus next year with me. This is where this negative 16. So this is kind of a standard equation for your gravitational pull with standard velocity and standard height. And so we're going to do a little bit of that as well. So this is called a parametric curve. It's a set of ordered pairs xy that's defined by parametric equations. You'll notice you have multiple equations. You have an x equation and a y equation where f of t and g of t are continuous functions of t or time on the parameter interval. All right? In this case, my interval was 0 to 2. So this is just basics of what is a parametric equation, and we're going to get into all of our conic sections, based on these. The first thing they want us to do is just draw a curve that's described by the set of parametric equations. They've given me my x and my y, and then they've given me a second set. We're just going to do one of them for time's sake. So we have an x and a y equation, and then they've given us this interval. Remember our notation here, this little looking funny e means that t is an element of this. Closed brackets mean that it includes -2, it includes +2, and it includes everything in between. Remember, time is continuous. It's not like you jump from 1 second magically to 2 seconds, right? It's a continuous growth there. So this is going to be a continuous function. We are going to pick certain numbers within it, and then we'll just complete the curve with a line. All right. And so you're going to set up a chart when you're just doing a basic one like this. You're going to say, well, I'm going to have a t input, and then I'm going to have an x and a y output, really. And that's going to determine my xy coordinates for this guy. And so typically you're going to use just easy ones to do. They did -2, -1, 0, 1, and 2, right? And so that's simple enough. We plug each of those into my functions. If I plug in a -2 into my x function, I'm going to get 2 minus -2 squared, so I'm going to get a -2 there. If I plug in a -1, I'm going to get 1. I plug in a 0, so on and so forth for x's. And then I'm going to do the same thing for my y. I'm going to plug in a -2 into my y function, -2 plus 1, -1 plus 1, and get all of those answers there. All right? These then represent my xy coordinates on my xy plane. All right? So we're not actually graphing three-dimensional here like we did earlier on with an xyz. We actually just have two equations that represent my different outputs, which represent my coordinates. So I'm going to graph these just like I normally would. I'm going to say -2, -1, 1, 0. That would be over here. 2, 1. You'll notice then that this is not going to pass my vertical line test because I have another 1, right, which is 2. And I have another -2, which is 3. all right? You'll also notice that I do not have arrows at the end of this. This is a closed bracket, so it doesn't go on infinitely, is what it's telling me here. So if I were to sketch this particular graph, I would sketch what looks like a sideways parabola here that stops, all right? My parabola stops. That is an example of a parametric equation and graphing it with this. All right, so let's try one. All right, so while graphing using your time input and output is fine, you can also eliminate that t altogether. And basically you're just doing substitution here to do this. So you're taking your two equations, you are solving one of them, whichever the easiest one is to solve for t, and then you're substituting that into the other one, so to eliminate your t variable altogether. And then you have a standard equation with an x and a y, and you don't have two separate ones. So if I look at this first one, I have x equals 2 minus t squared, and y equals t plus 1. And then t is an element of -2 to 2 inclusive. Eliminate the parameter and restrict the domain to generate the same curve as in example 1. So this was the same example that we had before, but instead of using my -2 to 2 and just plugging them in, I am actually going to eliminate my t altogether. When you do this, you want to do the easiest one to eliminate. For example, if I have this t squared and this t, I'm likely going to solve my y one because I don't have to do any square roots or anything in there. And so I am going to take this y function here, and I'm going to say, well, if y equals t plus 1, then t equals y minus 1. That's just basic literal equation, shifting my 1 over, okay? And now that I have that, I can take this guy and plug it into this guy for t, substitution. So we're going to say x equals 2 minus, and instead of t squared, I'm going to write y minus 1 squared, right? Basic substitution. Biggest problem here is going to be your negatives. So I'm going to do my square first. So I'm going to have y squared minus 2y plus 1. Don't forget that distributes through all of those. So 2 minus y squared plus 2y minus 1, and then combine like terms. So I get x equals negative y squared plus 2y plus 1. All right. And now I don't have a t at all. And if I graphed this, I would actually get a continuous sideways parabola here, which is what we got before, except it wasn't continuous. So to figure out then what needs to happen, I need to say, well, I have a couple things going on here. I have an x value is what I need to do my domain based on, right? Domain is my x value. And so I'm going to look at this guy right here, and I'm going to say, well, what happens then with him? So if I look at him, I'm going to set t squared by itself. So t squared is going to equal 2 minus x, right? I'm just taking this guy here. And then I'm going to say, what's the domain? Well, the domain has to be based on what my t represented, right? My t could only be from -2 to +2 here, right? -2 to +2. And so when that happens, I'm going to say, well, it can go from 0 to 4. Why 0? Okay, so if I just plug in my endpoints, here, -2 and +2 squared are 4, right? Well, inside that, I went -2 all the way to +2, right? So then I actually went through to 0 as well, right? Which is my smallest square if I plug that in. So this guy right here can be anything from 0 up to +4. Like if I look at a number line, my smallest value squared is going to be 0. My largest value squared is going to be either 2 or -2. It's the same thing squared, which means this has to fall in this range if my t fell in that range. So I'm going to say, well, 2 minus x has to be less than or equal to 4 and greater than or equal to 0 because my t has to fall in this. So my t squared must fall in that range. Does everybody see where I got my t squared value? I can't just do the endpoints here because it's squaring it. Can't just do the endpoints. I have to consider what my lowest value squared in there is, which is going to give me, how then do I solve for my x values? Well, this is a basic inequality. Subtract 2 from everything. -2 is less than or equal to -x, which is less than or equal to 2. My last step here is to divide by -1. What happens when I divide by -1 on an inequality? Algebra 1, what happens? I flip my signs. So 2 is greater than or equal to x, which is greater than or equal to -2, which means my domain, which is what they also ask for, is that x is between -2 and 2. By the way, it will not always be the same domain as your t. It just happened to work out for this one. It will not always work out that way. Okay, in fact, your example you're about to do doesn't work out where it's the same domain. Why do I have to restrict this domain? Well, this guy is going to go continuously. If I were to graph him, it is still going to be that sideways parabola, but I have little arrows on the end, right? Because based on this, it's going to go continuously to the left. However, my initial conditions restricted it. And my initial conditions said, nope, 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 you stop here and you stop here. Initially, my t restriction did that for me. -2 to +2. Initially, this guy restricted it, and I was done. Now that I've rewritten it without a t, I need to restrict it in the same way, but using my x values. And so that's going to restrict it with my x values there. My x values go from -2 to +2, and that restricts it there by putting that domain in there, that explicit domain. All right? Questions on that? Let's try one. So it says, given x equals 5 cosine of theta and y equals 3 sine of theta, eliminate the parameter and write the rectangular equation in standard form, then sketch the graph. So they've given us cosine and sine with an x. So really what we're going to try to do here is we are going to get the cosine by itself so that we are going to be able to use our trigonometric identities. I know that's a word that you just have been longing to hear again. So we are going to use trigonometric identities then to help set this stuff up. So I'm going to take each one of these and I'm going to say, well, instead of x equals 5 cosine of theta, what would cosine of theta equal? Well, that would be x over 5, right? Just divide both sides by 5, which means that sine of theta then would be y over 3. That's pretty straightforward. We can all do that. All right. Now, considering the fact that I am trying, and they specifically said ellipse here, not that you'll get that much information, but that I am trying to write, eliminate the parameter and write a rectangular equation in standard form. This means that I want to use one of my equations that I have been looking for. And so I am going to use an identity that deals with cosine and sine equaling something. So hopefully this is one that you have not forgotten. Hopefully you remember this guy right here, or vice versa. It doesn't matter. It is, it's the same thing. Sine squared plus cosine squared equals 1. All right? And so if that's the case, if cosine equals this and sine equals that, then I should be able to say that this squared plus this squared equals 1. That's logical, is it not? I mean, if I have cosine and sine of the same theta, they always square and equal 1. It is Pythagorean identity 101, right? And this actually gives me a standard equation. This gives me x squared over 25 plus y squared over 9 equals 1. What type of equation is that? When you have the x squared and the y squared and they're added together, it's an ellipse, which is what they're asking for, right? They're asking for an ellipse. And if I were to graph this, this would be an ellipse. It would be elongated which direction? Horizontally or vertically? Horizontally. How do I know that? My larger denominator affects my ellipse, right? My larger denominator. That's not true for hyperbolas, right? But it is true for an ellipse. So this is going to be elongated. It's going to be a stretched out circle elongated on my horizontal. And so if you were to graph that, it would be a pretty basic graph to do. You could find your vertices and all. Center at, where's my center here? 0, 0, okay? And so that's what we're looking at. We're going to try to identify, is there a way for me to write this using prior knowledge, all right? And so I will say Pythagorean identities are the ones you're going to see the most here because they add up to 1, or 1 squared minus this equals 1, or 1 squared minus 1 equals the other function with your tangent and secant and all. So if you have wiped those from your memory, you may want to go back in that file and pick it back up. So it says use each parameter to write a parametric equation for the graph y equals x squared minus 1. Think of this as going back the other direction. So we eliminated our parameters on example 2. They've actually given me the function y equals x squared minus 1, which is obviously a parabola. Hopefully you recognize that. And then they've given me time parameters to then go back in and write it as an equation that way, including your x and t's here. So we actually have the x function here. We're going to find the y function in terms of t is what we're going to do. So we're just going back the other direction. In 2, we were taking the two parametric equations, getting rid of the t and writing it as 1. They've given us the 1, and part of the other one, we're going to find the other guy. So we're going to use this same function every single time for all 3 of these. On the first one, they actually have my x by itself. So that's easy. I'm just going to go ahead and do substitution. I'm just going to take this and I'm going to say y equals, and instead of x, I'm going to say t squared minus 1. Very simple when I have it like that. When I don't, so if I look at the next one, I don't have x by itself, so I just need to get it by itself. I'm just going to subtract my 1, multiply by my 2. There we go. And then I'm going to do exactly the same thing, y equals, and I'm going to plug this guy in. That's a minus 1 there. Simplify it. And then I have my, that should be 8, 14, 4t squared minus 8t plus 3. And then that is written. I have my x1 and my y1, which technically this is my x1. All right, so we're basically just using what they gave us and to split it up into two parametrics is all they're doing. We're just going the opposite direction here. They've given us my equation. They've given me one of my parametrics, and I'm finding the other one using that guy with substitution. All right, so really quickly do one of these, only once. I just want to point out that when you write your parametric, you'll notice I underlined the ones. You should have an x parametric and a y parametric. And then your element now, your domain is now written in terms of t. Okay, so all they did was they took the -2 to +2 and they plugged it in here. So -2 plus 1 gave me my -1. +2 plus 1 gave me my +3. You have your new values for your domain here. So think about parametric, your input is your t value. That's what you're going to tell me your restrictions on. Your standard equations without your parametric, your restrictions are on your x. Your domain is your x. So all they did was they, just like we went the other direction and took our t and found our new domain with x, you should have taken your x and found your new domain with t. Okay, so that's why they have this little added piece here, because this does not limit it enough. Okay, that doesn't tell you your limitations on it. So you have to list your new limitations with your new input. It says write a set of parametric equations for the hyperbola with vertices at 1, 5, 1, -1, foci at 1, 7, 1, -3. All right. So if I want to find my center is really easy. I'm going to take my vertices and just do my midpoint, right? So center is really easy. I'm going to take this guy and just do midpoint. Midpoint, when it's the same value, is that value, right? The average of 1 and 1 is 1. And then for the other, I'm going to say 5 plus -1, or 4 over 2. So my center is going to be at 1, 2. I just midpoint my vertices. That's simple for my center. The other thing I have to do is I have to figure out my A value, B value, A and B value, so that I can set up my equations, right? My center is half the battle. I have my H and K, but I do need my A and B to set this guy up. And so again, you're going to look at how far away from center am I moving. My A value is going to be how far away from center I am moving to my vertices. So my A is how far I'm moving away from my vertices. My C is how far away this guy's moving from my center. So center is going to tell me my A value if I have my vertices, and my foci will tell me my C value. All right. Well, how far away from A am I moving, or from center am I moving from my vertices? Well, I'm moving 3 away, right? 2 plus 3 is 5. 2 minus 3 is -1. That's how far my A is. My C then, how far away is that guy? Well, he's 5 away, right? Everybody see that my C value is going to be 5. That's my foci. If I have my A and C, I should be able to find my B value, right? Should be able to find my B value. C squared minus A squared. So I have 25 minus 9, square root of that. My B value is 4. Basic Pythagorean there. Okay? So if I have my center, my A, and my B, I actually have my function here. All right? I have my function. Which one's going to be negative? With a hyperbola, my negative indicates my positive indicates which direction it's going. All right, so if I know which direction it's going, I can figure out whether it's going to be minus or plus here. My y value is what indicates which way it's going, right? If my vertices go up and down, that's going to be my y. If they go left and right, that's going to be my x. So my positive here is going to be in front of my y. Remember, with a hyperbola, your h and k's don't move. Your h stays with your x, your k stays with your y. So it's going to be y minus my h value, which is 2 quantity squared, right? Over my value of my a squared, 9. It is going to be minus. And then my h stays with my x value over my b squared. And that equals 1. All right? Questions so far on that? Now they flipped back and they wrote it in tangent secant form because now they want parametric equations. This is my standard equation, okay? This is my standard equation here. And so if they say they want a set of parametric equations, this is going to be a booger to get x by itself and y by itself. Do you agree? Like, I don't want to get x by itself, personally. Okay, I'm going to have a ginormous. So we're going to actually work backwards like we did in example 3. In example 3, we were given trig functions and we said, how do we set it up in a plus minus squared so that we can have a standard equation here? Here we have a standard equation and we want parametric. The easiest way to get it into parametric is to rewrite it, meaning secant equals 1 or tangent equals 1 or sine equals 1 or cosine equals 1. All right, I automatically know it's not sine squared and cosine squared. Why? Because I don't have a sine squared minus cosine squared equals 1. I don't have that. I do, however, have tangent, cotangent, secant, and cosecant that I can deal with, okay? And so in this case, I have something squared minus something squared equals 1. And that's going to go back to secant and tangent. So if you will recall, hopefully, tangent squared plus 1 equals secant squared, right? Which means 1 equals secant squared minus tangent squared, right? That's what I'm looking for when I have a subtraction. I'm going to use my secant and tangent. When I have an addition equals 1, I'm going to use my sine and cosine. When I have subtraction, the easiest way to rewrite these is to say, well, this one must be one of them, this one must be one of them, all right? So in this case, which one is this? If this is my formula, this squared minus this squared equals 1, which was this one? That's going to be secant. So secant squared of theta must equal y minus 2 over 3 squared, which means secant of theta equals y minus 2 over 3. All right? And we're going to simplify him in just a second. This guy must be tangent squared, which means tangent squared of theta equals x minus 1 over 4 squared, or tangent of theta equals x minus 1 over 4. All right? Now, a true parametric has my x by itself and my y by itself. This is way easier to get x and y by itself now than this guy, okay? This is impossible to get x and y by itself without a bunch of finagling. This is very easy to get x and y by itself. Everybody see that? And so those are the two basic ones you're going to be using. X squared plus y squared equals 1. Sine squared plus cosine squared equals 1. Something squared minus something squared equals 1. Secant squared minus tangent squared equals 1. Those are really the two that you're going to be using with these because that's what you're going to find. All right? To get it by itself, this is basic algebra here. Multiply by 3, add 2. So y is going to equal 3 secant of theta plus 2. X is going to equal 4 tangent of theta plus 1. If you look above it, you will see the basics of the parametrics when you involve motion on a plane. And I don't mean like an airplane, but like a plane. So you have your x value. That should look familiar. Your vector times cosine of theta. That's x. But now we have times t. So we're throwing in a parametric. For my y value, this is a little bit different. We have 1/2 my gravitational pull, and we'll talk about that in a second, t squared, plus this is my actual initial velocity, which also should look familiar. My vector sine theta is my y value times my time. And then we have an initial height. Gravitational pull, 32 feet per second squared for feet, and then 9.8 meters per second squared for meters. So that's something you just need to know. If you haven't used it enough in physics, you need to memorize that. All right, so let's look at this. Julie throws a ball at 1 foot wide circular dunk tank target that is 30 feet away, whose center is 4 feet above the ground. She releases the ball from a height of 6 feet with a 10-degree angle of elevation and a speed of 50 feet per second. Write a set of parametric equations modeling the ball's trajectory and determine whether the 4-inch diameter ball hits the target. You need to know this, and you need to know that gravitational pull in feet is 32 feet per second squared, or 9.8 meters per second squared. You need to know that. Memorize it.